In section 4.3, we're going to look at how to solve linear second-order homogeneous DEs with constant coefficients. So what we're talking about are DEs that look like this. So we can see that it's linear, it's second order, it's homogeneous because on the right-hand side here we have 0. And the coefficients of y and its derivatives are all constants. So 1, 2, 3, 4, 5. We started looking at these yesterday. We saw a couple of examples, solutions that that we found involved cosines and sines and e to the x's. So we're going to start with a guess, and that guess is going to be, well, maybe it looks like an exponential. So a solution should look like y equals e to the rt. Okay, we'll work with this and see what happens. Okay. The reason that we have this r is that we know that when we're taking derivatives, we will have constants generated, and so we have some hope that we might be able to match up with these coefficients a, b, and c. Okay, so here r is a constant that we don't know yet. So let's try working with this solution. So y equals e to the rt. Its derivative is r e to the rt, and its second derivative is r squared e to the rt. Okay, when we substitute it into the dE, we get r squared e to the rt plus, or times a, plus b times r e to the rt plus c times e to the rt equals 0. So we're a solution if the left-hand side is equal to the right-hand side. Notice that we have e to the rt in each of these terms, so we can factor it out. We get ar squared plus br plus c, and times e to the rt is equal to 0. So if you think back to how the exponential behaves, we know e to the rt is always positive. It's never equal to 0. So we can divide by it, and we get ar squared plus br plus c equals 0. So what's our conclusion? Our conclusion is that y equals e to the rt is a solution to the dE if and only if. So exactly when r is a root of this quadratic polynomial p of x equals ax squared plus bx plus c. We call this polynomial the auxiliary equation for the dE. So we're going to start by practicing finding auxiliary equations, and then we're going to look at the solutions they generate. We know that for a quadratic polynomial, we can either have two real distinct roots, we can have one repeated real root, or we can have a pair of complex conjugate roots. So we'll look at the solutions for each of these three cases.